Hi, our group is presenting on ultra-precise clocks. So what is ultra-precise clocks? Quantum logic clock measures the vibration frequency of UV lasers. To keep the lasers time keeping precise, its vibration must be anchored to something much more stable. That anchor is the vibration of electrically charged aluminum atom, which vibrates at 1.1 petahertz or 1.1 quadrillion times of a second. The first step in measuring the ion vibration is to help with UV lasers, which are tuned to charged atom rate of vibrations. Precise clocks have many uses within the scientific studies. For example, it is certain where incredible precision is needed to sync their atom-smashing instruments. But atomic clocks are also used within the world we experience every day, including the internet where exact timings are critical. However, they are probably most common for the uses within the global positioning system or the GPS. For a GPS satellite to work out our exact position, the timing of the signals needs to be sent and received at the speed of light, which means that even a single microsecond error can translate to around 300 meters error on the ground. The timing has to be so well controlled that even tiny effects because of the relativity needs to be tracked.
Now allow me to explain how clocks work. Then we can jump right into how ultra-precise clocks work. Think of the grandfather clock. It has a pendulum that rises and falls. Its motion can be mapped like a sinusoid, as shown in the figure in the right. Each time the pendulum makes a complete cycle, we increment the clock by 1 second. The period is the time it takes for the pendulum to complete one whole cycle. And the frequency is how many cycles the pendulum can complete in 1 second. This means that if we have a higher frequency, we can record time units smaller than 1 second. And for each pendulum swing that's been completed, we can increment our clock by 1 tick. We call this a tick simply because it is an increment of the counter which we are using to determine time. As the smaller the gap we create between each tick, the less margin of error is found. Now let's talk about the predecessors to the ultra-precise clocks, the atomic clocks. Atomic clocks monitor the energy level of a specific atom. It can be any atom, but for this example, we will consider cesium. From experimentation, we know there are two states that a cesium atom can be in: high, otherwise known as excited, and low. First, we take an oven and heat up our cesium atoms. Then we want to segregate the high state atoms from the low using a magnetic filter. As you can see in the figure, it's the first magnetic filter is in the left-hand side, right before the chamber. Next, we will have the microwave radiation chamber fill up using the separated atoms. And the microwave radiation chamber will bombard the low energy atoms using radiation at a set frequency in order to convert all the atoms into the high energy state. This conversion process happens at a set frequency. Using the magnets again, we can divert the atoms into a detector. Only this time the detector will be accepting the high energy state atoms, as opposed to the previous detector which only accepted the low energy state atoms. Now, the basic concept is that each time a high energy atom is detected, we can increment our clock counter. Since microwaves have a very quick frequency, we can measure ticks down to the accuracy of 3 times 10 to the power of minus 16 seconds. That's why every 100 million years, the cesium atomic clock will be off by 1 second in accuracy. That is pretty impressive. The detector in this model will supply a feedback loop to our chamber. This is done to allow the adjustment of the frequency of the microwave due to the uncertainty of change in the energy state. This is basically used as a correcting mechanism. Finally, we can talk about the ultra-precise quantum clocks and how they work. This diagram that I've drawn is a very rudimentary diagram that we have made to simplify the process. The ultra-precise atomic clocks work as following. There are 4 main components to show from left to right: a laser to excite the ions, an aluminum ion, a magnesium ion, and a second laser to observe the motion. To keep time, quantum logic clocks measure the vibration frequency of UV lasers. That is a laser you see on the left-hand side with the red wave coming out of it. However, due to the fact that lasers can go off course every 1 hour, they are not a very reliable or stable instrument to use. So, to account for this, an aluminum ion, which was to be observed initially by itself, must be coupled with a magnesium ion. This is done so that when the laser is shone on the 2 ions, we can measure the motion of the spinning magnesium ion. That is simply due to the fact that a magnesium ion emits a light of photon once it is excited. If the laser misses, then just like the cesium clock model, the observer laser will tell the exciting laser to readjust itself. This is especially useful for cases where the laser has gone off track and our computer is unable to identify its original position. In summary, the only major difference between the ultra-precise clocks and the atomic clocks is that the ultra-precise clocks can measure ticks at a higher frequency using lasers. And in order to achieve this, atoms like aluminum must be used because they are easily excited at a higher frequency rather than cesium or any other atomic alternatives. You may be asking, why don't we simply use magnesium ions and ditch the difficult to observe aluminum ions altogether? Well, this is because magnesium ions jump to their excited state at very low frequencies. That is why they're simply used as a control group. If we only use magnesium ions, the precision of our clock model would be very poor in retrospect to using aluminum ions. So we mix the best of both worlds using aluminum ions and magnesium ions.
Atomic and quantum clocks are designed with some of the basics of quantum mechanics in mind. Firstly, the magnets that the atoms pass through to separate them by their energy states is very similar to the Stern-Gerlach experiments, where they use magnets to determine the spin of a particle. Secondly, the measurement of the oscillations of the atoms is actually a measurement of how many times the atom is alternating between a ground state and an excited state. These energy states are discrete and require a specific amount of energy to transition. Whenever the atom transitions between two energy states, it emits electromagnetic radiation in the form of microwaves, which are then captured to detect these changes. By first passing the atoms through magnets and filtering out ones already in an excited state, only atoms transitioning from a ground to an excited state have to be considered. However, due to the uncertainty principle, by measuring the state of the atom, we increase the uncertainty in the measurement of its oscillations. The oscillations of the atoms are averaged out to get something closer to the correct value, but there's still going to be some imprecision. Since the oscillations of the atoms are used to calibrate the clock and measure time, this poses a huge problem. Recently, the use of a technique called quantum entanglement has been used to try to get around this. It combines the atoms in a single entangled state, with all their properties linked. This increases the uncertainty in the measurement of the state, and at the same time it decreases the uncertainty in the measurement of the frequency, allowing for a much more precise clock. The fluctuations in timing for this improved clock have been shown to be reduced by as much as 3 times.
Ultra-precise quantum clocks are very precise tools that allow us to measure time with an immense amount of accuracy that goes even further than what the previous atomic clocks were able to achieve. There are many advantages that arise from this increase in precision and accuracy that ultra-precise quantum clocks provide. The first advantage is the fact that ultra-precise quantum clocks are very useful in the measurements of time dilation. This being said, it allows us to measure Einstein's theory of general relativity with a great deal of accuracy. It also allows us to indicate and get a better feel for how much gravity actually warps time. In general, as the clocks are moved higher up, the gravitational pull on them is decreased, which allows them to tick at a faster rate. And if the clocks are moved closer to the Earth, then the gravitational pull on them is increased, which causes them to tick at a slower rate. Ultra-precise quantum clocks are measurement tools that can map the shape and size of the Earth and provide this measurement with only a centimeter or less of error. This has direct consequences as a result. One of them being it allows geologists to track the movement and monitor tectonic plates on Earth. It also allows climate researchers to monitor the rise of the sea level and track other events that have direct relations to climate change. One way we can track the effects of climate change using the ultra-precise quantum clocks is to take them and pair them up with a gravimeter on top of mountains that have permafrost inside of them. As the permafrost begins to melt due to global warming and climate change, we can accurately provide height measurements with up to 1 centimeter of error. This would indicate the rate at which the permafrost is melting and directly provide information regarding the impacts of climate change. Another advantageous use of ultra-precision quantum clocks is their usage in GPS satellites. GPS satellites have multiple ultra-precise quantum clocks within them. Each one of these clocks contribute extremely precise time data, which is sent as a GPS signal to our respective GPS receivers on the consumer side. The GPS receivers then proceed to decode these signals and can provide very accurate time data, which in turn allows us to triangulate our current location to a great degree. Using ultra-precision quantum clocks, we will be able to triangulate our position within 3 centimeters of error. As time goes on and technology advances further, the clocks will become more and more precise, which will allow us to tell our position better and better utilizing GPS. Some other advantageous uses of the ultra-precision quantum clocks include the ability to take certain dark matter models that we know, set our constraints for this type of model, and then search for these models within the universe. Another one is the development of these ultra-precise quantum clocks also assists in the resolution of constants used in physics, such as Planck's constant and the speed of light within a vacuum. This allows us to further investigate these constants with greater precision than we ever have before. However, there are still some disadvantages involved with ultra-precise atomic clocks, based on limitations on the technology and advancements of the technology. To start things off, one big restriction is the geographical location of the ultra-precise quantum clock. It's quite difficult to decide where the best place would be to place the clocks because of the following. If we put the clocks too high, then the gravitational effect on the clock will decrease and cause the clock to tick faster. If we put the clocks too low, then the gravitational effect on the clock will increase and cause the clock to tick slower. This means that the international standard definition of a second will be based heavily on the height at which the ultra-precise quantum clock is placed. Another restriction is based on the atmospheric conditions on the receiving or consumer end of these ultra-precise quantum clocks. Transmitting the radio waves from the ultra-precise quantum clocks to a consumer device is based on a variety of factors that can cause differences in time between certain individuals. If a consumer atomic clock is receiving the radio wave from the time signal stations that house the ultra-precise quantum clocks, factors such as the direction in which the consumer is facing and interference sources play a huge factor in the signal sent. Atmospheric conditions such as low-lying fog and high-pressure areas can also impact the reception of these radio waves from the ultra-precision quantum clocks. Another restriction is the distance to and from the ultra-precise quantum clock itself. When it comes to transmitting the radio waves sent by the time signal stations, the wave would take time to reach the consumer's ultra-precise quantum clock. This would cause discrepancies between the time the signal was sent from the time signal station and the time that the consumer's atomic clock received the signal. That would be slightly later in this case due to the time it takes to travel for this radio wave. In general, the farther that you move from the time signal station, the greater the inaccuracy the time received will be. This causes drastic effects on the west and east coast of Canada as you move further and further out. One of the major downsides is that it is difficult to advance the precision as to which ultra-precise quantum clocks measure, since there is a great deal of difficulty in measuring the ticks per second of clocks that are more precise, since the definition of a second of time is currently based on the cesium fountain atomic clock. In essence, the cesium fountain clock has difficulty in providing the precision of the ultra-precise quantum clock, since the ultra-precise quantum clock is in fact more precise than the cesium fountain atomic clock. This poses issues to this technology's advancement as time progresses forward. It is quite difficult to update the international standard definition of time and the international standard definition of a second of time, since many of the aforementioned restrictions play a factor in this and cause impacts. These aforementioned restrictions are the geographical location, the atmospheric conditions, and the distance from the source ultra-precise quantum clock. The distance can be slightly negated through the use of fiber optic cables to relay the information regarding the time data. The only issue is this is only good up to a distance of 60 miles.
Even as ultra-precise clocks are able to measure smaller and smaller intervals of time, there are hard limits set on how precise they can get. Though it's far smaller than any unit of time that has been measured today, a unit of Planck time, which is equal to approximately 5.39 times 10 to the negative 44 seconds, sets a cap on quantum clocks. Any smaller division of time doesn't have any meaning, and our current understanding of physics no longer applies. For example, the geometry of spacetime predicted by general relativity breaks down. Since our current clocks are based on our current physics models, they would no longer work at this scale.